Okay, very good. So we are very pleased to have MaElena Tejeda Yeomans here with us today to talk with us about lambda baryons in very intense situations. MaElena she got her bachelor's degree in Mexico. She moved to the UK, Durham University, to get her PhD, and then did a postdoc at Stony Brook, and then accepted a faculty position back in Mexico. And and the reason that we invited her to give a talk to us today, it was all down to Twitter. So there's like subgroups of Twitter, sub-communities of Twitter. There's physics Twitter, STEM Twitter, and MaElena and I are both in the physics Twitter community, which of course is open to anybody. And there was this joke going around, MaElena probably won't get it right, but there was this joke going around at one point saying electrons are not real. They're like a conspiracy by big physics to sell more copies of Michael Peskin and Daniel Schroeder's quantum field theory textbook. And I'm not doing it justice, but it actually was very funny. And so I happened to be in a conversation with Michael Peskin at that time talking about QCD potentials. So I screenshotted it and sent it to him because I thought it would make him laugh, and it did. But he noticed who retweeted it. He said, MaElena Tejeda Yeomans is one of the top perturbative QCD physicists in the world. If you don't know her work, you better look her up. And so I did, and that's why she's giving us a talk today. MaElena, okay, so I'm very happy that you accepted our invitation, and please begin whenever you're ready.
Oh, thank you, Jennifer. I think with that presentation, things could go either too good, too well, or too bad. I don't know, depending on the on the standards that you imagine this will be. Given the discussions that we had to come to this point in me presenting this work with Jennifer, and given the interest that she had, you had, Jennifer, very particular questions. I'm trying to make a presentation that includes some like general ideas about Lambda, and I'm going to make an effort to always mention anti-Lambdas as well, and you will see why in the results section. Their polarization and the role that the measurement of polarization for these hyperons is taken these days as many people by one of the possible promising signals that we can continue to use to characterize the QGP, but now in a more like modern approach, thinking about the new scans of the QCD phase diagram and all these things. The polarization of lambda hyperons could, very well be a precise measurement rather than some measurement to characterize hyperons like it was in the past. So my talk is going to include work that I've done in collaboration with many people, but in particular, I've recently worked in a core corona model to try to understand some features of this polarization. And I worked with Alejandro, Isabel, and Yvonne Maldonado. So towards the end of the talk, I'm going to show you what we got so far. So the first half of the talk deals with these general aspects of the role that strange baryons play a long time ago in the building up of the actual standard model, but then the role that the strange baryon play nowadays as a QGP signal, and how the polarization of lambdas has helped recently to characterize one particular property of the QGP. But I'm also going to highlight towards the middle of the talk what are the theoretical ongoing or pending efforts that we can see that we can work on and maybe help in some of the issues that are pending in this area. And for those of you who can stay for the complete talk, maybe you will get to hear about how we built this model, this core corona model, and what are the ingredients of this model, and what are the main results we can get with this model in comparison to other models. And of course, what are the limitations or next steps that we identify already we're working on for this. So let me start somewhere, and the place that I chose to start is with this phenomenal article paper by Li and Yang, where they question parity conservation in weak interactions. And in particular, they built an argument where parity non-conservation in certain kind of processes implies the existence of interactions where there's a mix of parities, and therefore where we expect an asymmetry in the way that the nucleon, in this case the proton, is produced in space. It's the distribution, the angular distribution of these products of the decay of lambda. Actually, if we follow where these protons are flying, they say, well, actually, if you do that, then you'll discover that there is a contribution that is not a flat contribution in this angular distribution, as you would expect if there's a complete symmetry or parity conservation. And this asymmetry in the angular distribution of the proton as a product of the lambda decay actually has an intensity that is controlled with this parameter alpha, which was back then called the decay asymmetry parameter by these guys. And so the prediction in this paper was that if you measure this quantity for a specific, they made a proposal on beta decays and hyperon and meson decays. If you measure this quantity and if you find that alpha is different than 0, then this would be a proof or a test of parity non-conservation. And in fact, this paper is a seminal work, and it provided the grounds for many years after the paper for many measurements in order to look for the this alpha parameter, to measure this alpha parameter, if indeed this was correct. I found that it was pertinent that I chose not any measurement, but an actual measurement that was performed at your lab. Back then it was just the radiation lab. Of course, now it's LBNL. And this measurement was performed immediately the next year after this paper was out in 1957. They used a 10-inch hydrogen bubble, and they had the production of lambda and sigmas in this kind of bubble chamber setup. And it is nice that the open access of the University of California lets us see the way that it was reported back then. It was reported with the same notation that Li and Yang were using in their paper, where they propose how to create a pseudoscalar quantity that could be measured, built in terms of the center of momentum of the incoming pion, the center of momentum of the produced lambda, and the projection in the decay in order to get information of this, let's say, the polarization intensity. And indeed, they report that they had photographs for 76 double V0 events, which is the signature of the decay, which is 2 charged particles coming out after the decay, and 277 single events where they only observed this lambda decay. And with that data, back in 1957, they produce an estimation of the alpha parameter, which was around 0.44, which is already different than 0. And it just gives a very nice example of one of the earliest measurements of this anisotropy in the angular distribution that emerges in this kind of parity violating decays. Another thing that is nice that you can look up is the fact that this quantity, if you go to the PDG nowadays, after many measurements using many different setups, you will see, and I will mention it in the next couple of slides, this quantity is as big as 0.7 nowadays with all the data that we have. So it is a big anisotropy, and it is a different. It's the starting point of this discussion that we will have today. Now, I also found very nice that the leader of this, let's say, measurement, Crawford, back in 1957, is the same Crawford I didn't know up until I was creating this talk. Is Frank S. Crawford Jr., who is the author of one of the Berkeley physics series books that I used when I was an undergrad. All of them, I use all of them. So I think it's quite nice that there's a connection between the way we learn about, in this case, waves. This is the Spanish version of that book. So if you go to the PDG, you'll realize that there are many advantages of using lambda particles to study these kinds of parity violating decays. But the advantage also that we have, given that the lambda produces two charged particles in the main decay channel, so 2/3 of the time it goes to a proton and a negative pion. The advantage that this is the main decay channel is that it is fairly easy with the tracking detector to reconstruct the properties of the lambda by filtering, of course, the products of the decay, by making correlations with the vertex of production, the vertex of the decay. And I think it is quite nice that if you look at the PDG, you'll find that there are very nice small error bars to the mass of the lambda. And of course, the lifetime, which is another advantage for this kind of particle. It has a fairly large lifetime compared to most of the lifetimes we're used to. And this makes let's say the average path length that the lambda goes through before decaying, a fairly sizable size. It's around 8 centimeters. And so in a decent, not too big fiducial volume of a detector, you can capture the complete process as back then was not in a bubble chamber, but as it is done nowadays with a TPC. By the late 70s, let's say, lots of measurements were done on this same kind of process, but now instead of using a very particular setup like Crawford team did back then, now people started using all sorts of hadrons hitting nucleons, nucleons hitting nuclei, and nucleon hitting another nucleon in different versions at different collision energies at different fixed target situations. And immediately the amount of data that people had before the 80s was building up a series of ideas that only increased when people started thinking about finite temperature, finite density system made out of quarks and gluons. So by the early 80s, lots of people, but I choose to talk about the work by Rafaelski, which was also seminal in these kinds of ideas. By the early 80s, he was discussing how, if we can create this high temperature phase of QCD, which is very peculiar, it contains very nice properties of color deconfinement. Back then there were like, ideas and some restoration of chiral symmetry, some phase transitions. If we had access to this kind of system, he claimed back then in the early 80s that automatically there were conditions to have the production of strange quarks in a more efficient, let's say, way in this QGP than in the regular non-QGP situations. And he gave a list of arguments that I've just, you can see the historical development of those arguments in this recent manuscript written by him, where he goes slowly through the evolution of these arguments. But basically, back then, they were saying, well, if you have the QGP, and indeed, if you have quarks and gluons behaving like in this deconfined phase, and you have access to lots of energy, then in principle, you would have these fundamental processes, gluons fusing into pairs of strange quarks, or quark anti-quark going into this pair of strange anti-strange quarks. These basic processes, basic QCD processes, in this medium, in this hot medium, indeed, they only require at least the mass of the strange quark, twice this mass, in order to be starting to produce these strange quark pairs. And if you think about it, when you compare the situation with the traditional nucleon-nucleon collisions or hadron-hadron collisions, or usually you need to break this threshold, which is way higher in this case, because you need to produce lambdas and kaons, depending on what process you're focusing on, which actually needs way more than a couple of hundred MeVs in order to be able to produce strange baryons. Now, on top of this, the other crucial, I think, very important argument that was done I think it was with great hindsight and imagination that this was done back then, but it has become something that we can now test, and we can now see that it does happen, is the fact that anti-strangeness can be more abundant than anti-ups or anti-downs in this QGP. And there are several arguments that you can give, which together take you to this conclusion. For example, if you think about the initial condition to create this QGP, usually is some nuclei that are collided at high energies, which are made of protons and neutrons. So in principle, there is no strangeness in the initial condition. So, or the quality of the system that is created has actually no net strangeness. So the phase space available for anti-strange is not suppressed, whereas it is suppressed for anti-ups and anti-downs when you think that you're producing this QGP in a situation where you have finite density in the system. I will come back to these points, and of course, maybe I'm saying it too fast, but altogether, these arguments back then were crucial to think about, but nowadays we can test that indeed strangeness, or in fact strange baryons are produced in these systems with a lot more frequency than in others. I will show you in a minute. Now, the other crucial argument of strangeness, this enhanced strange baryon production, as was done back then in order to build an argument of how this baryon production could be a QGP signal, was the fact that when Rafaelsky and Mueller got together and calculated the actual cross sections of these fundamental processes and included gluon fusion in particular, the conversion of gluons into a pair of strange and anti-strange quarks, they realized that in fact including this contribution helps understand that indeed the abundance of baryons with strange quarks can happen for a QGP that has a particular lifetime, and in a way, strangeness can be in thermal equilibrium in this new medium, independently on for a wide range of temperatures of this created medium. So you can calculate the time evolution of this abundance, and you realize that you indeed have a survival of this abundance, even though the lifetime of the QGP is not that bad, is not that big when you think about it. And they reported the rates of these several processes, the rates of conversion of any quark anti-quark pair into strange anti-strange, and also of the gluon fusion channel. And they did it for a range of values for alpha strong back then, and for masses that were not as close as the masses that we know we have measured now for these quarks, but still the result holds, and nowadays we have evidence of that. Immediately after this work was done, people incorporated the production, the enhanced range baryon production as part of the programs to look for the QGP. And in fact, if you check out the long range plan for nuclear science back in the 90s, they made a list of signatures of the QGP, which have the traditional list that incorporate the behavior of temperature, the looking for chiral restoration with chiral partners, parton propagation. There's also signatures that are missing here because back then there was no idea of the impact of flow and all of these critical measurements that we have now for the QGP, but stranges was one of the main ones. So the enhancement of strange baryon production was in the list back then. And we can see, actually, I'm gonna just go to the next one so you can see both. We can see the yield of lambdas and other baryons, strange baryons, produced at RHIC energies, 200 GeV, and going low in this scan, also with lead-lead collisions at mid rapidity, going down to 17.3 GeVs, and you can see that the amount of lambdas and other strange baryons relative to the amount of lambdas and those strange baryons producing either PP or other kind of reactions, which is this one here, is actually almost reaches 10, this ratio, this yield relative to PP for gold-gold collisions and lead-lead collisions at RHIC energies. And on the right, you can see a more recent report done by Alice, where they actually managed to summarize the behavior of the ratio of yields of several kinds of strangeness hadrons with respect to the multiplicity of the events. And this is very nice because multiplicity can be connected to many properties of the events. It could be connected to centrality. It could be connected to and many other qualities of the QGB that is being created in these systems. Anyways, so I just wanted to show that indeed this was discussed back in the 80s, but experimentally is well established as a, so the enhanced strange baryon production is well established as a QGP signal. So if I now come to the current situation, we have plans for to scan the QCD phase diagram in temperature and net baryon density. And as far as we can tell, there will be an overlap between, there is an overlap between RHIC-based scans and other scans that are being planned or done in this moment to look for not only these phase transitions, but also look for some appearance of criticality in the systems. And the wealth of knowledge I tried to synthesize, not very successfully, is a list of many, many things. I'm just highlighting the ones that I think are relevant for this talk. For example, we now know that quark flavor equilibration happens. And so we can say that strange quark pairs are produced as abundantly as up and down quark pairs under certain conditions, of course. Hadronization, for example, happens when quarks recombine into hadrons once the system cools down. So given that you have an initial condition, this very nice picture by Chun Chen and Heinz, when you have the initial condition and you have the initial system, it evolves through a phase, hydrodynamical phase, let's say, and eventually you have conversion or recombination of quarks into hadrons at a certain temperature that is usually characterized by this Hagedorn temperature. There are fluctuations and correlations in these quantum numbers that are carried by quarks. So event by event, you can see some drastic changes in some properties, but the global picture might be different than that you get from events analysis. We also know that in this hydrodynamic phase, we learn a lot about how the viscosities, in this case, I'm making emphasis on the shear viscosity, how it gives us an idea on how the QGP flows and what are the patterns of this flow. And there's a connection between the properties of the QGP and the lowest fluidity given by this very small ratio of viscosity to entropy, and many, many other things that we know already and that have helped us establish a standard model of heavy ion collisions. Given that we want to explore this diagram, and given that we know a lot about lambda polarization in the context of the regular nucleon-nucleon collisions, but also in the context of the creation of the QGP, suddenly there is a new role to play for the lambda polarization in order to characterize further the QGP. And I'm just going to make a parenthesis because it's a very nice example of how different fields of physics can, I don't know, influence each other or inspire each other. So right about the end of 2015, early about 2016, it was reported that there was the first observation of the coupling between vorticity in a fluid and the spin, in this case, in this particular experiment, in the spin of the electron. And these, Takahashi and collaborator performed like a macroscopic experiment where they have a tube and they have, I think it was fluid mercury going through this tube with some particular characteristics to make the flow in the presence of some finite amount of viscosity, so that in this kind of flow they create vertical regions, given that you have the walls of the tube and you have some amount of shear viscosity, you create vorticity, and this vorticity helps align the charge carriers in this fluid in a particular way so that they either align for the vorticity that is looking down in this diagram, or the vorticity that is looking up. This kind of segregates charge and it creates kind of like a current. And this kind of idea of the coupling between the vorticity of a fluid and the spin of the electron was already being reported by 2016, came together with the development of ideas of further characterizing the QGP, the fluid phase of the QGP, using similar tools. I'm going to summarize what happened in the early 2000s. Basically, Liang and Xinyang and all collaborators, Beccatini later in 2008, and finally Xiang and Lin and Liao in 2016. Throughout the 2000s, there was a huge development of ideas where people were proposing that there should be some kind of way to learn about the polarization of the QGP if we recover the information that, for example, lambda hyperons have with regards to how they become polarized when they are produced in this QGP. The development of this hydrodynamical model that I briefly mentioned helps further this idea, because in the context of hydrodynamical model, you can have control over the velocity fields and the vorticity that you create with these fields. So immediately there were proposals of how this vorticity could provide polarization to lambda hyperons with different frameworks. And finally, in 2016, there was an actual proposed experimental case study for RHIC, which was picked up and was implemented. And so in 2017, the STAR collaboration reported that indeed they managed to provide the further characterization of the QGP through its vorticity, extracted from a particular measurement of the polarization of lambda hyperons. And what they did was to consider the collision of two nuclei, and include in this picture of collision of nuclei the situation in which the overlapping region of the collision is whirling around, and it has some amount of angular momentum, and appealing or making some kind of proposed coupling between the sort of mechanical vorticity that you introduce, the amount of angular momentum that you have at your disposal. The question was whether we can connect this with the properties of the global polarization of the lambda hyperon. I'm not going to go deeply into the details of the measurement. I'm just going to say that it relies heavily on the first ideas that were done, that I reviewed at the beginning, where again, you're looking at the angular distribution of the protons that are product of the lambda decay, and you're looking for the amount of polarization that is associated, or the intensity of this polarization that is associated, that you can extract from these angular distributions. And you do it in such a way that you imagine that you have this event plane, and you have this certain amount of angular momentum, a preferential direction of this angular momentum, which is global, related to the event. And in that particular way, you can project out the information of the polarization and include all the corrections due to the resolution of the detector, and so on and so forth. And from there, they could have a prediction or a measurement of the average polarization of primary hadrons that are emitted from this situation that has a particular vorticity. And this vorticity is estimated to be 10 to the 21 per second, almost 10 to the 22. Back in this paper, which was amazing when it came out, and it still amazes me how experimentally you can give an estimate of this vorticity, assuming many things, of course, because now we know that this is kind of like a global characterization of the system. But in any case, you have a tool which is lambda polarization, and from there you are extracting the properties or the whirliness of this system that you're creating. Now, that is to set the context. Now, from that paper, there are two amazing things that happen. They reported the polarization of lambdas and anti-lambdas in two ways. First, they reported it with respect of the collision that you have, the energy of the collision, which goes from 7 to 100 or less than, from 7 to around 200 GeVs in this range. And you have on the left the report for gold-gold collisions in 20 to 50% centrality. You have the blue symbols for the lambdas and the red symbols for the anti-lambdas. And there's an update in the data from back in 2007. And on the and you see that with respect to the collision energy, you have kind of like an erasing of the polarization when you go to high energies, and some enhancement when you go to low energies around 7 GeVs. And another feature of this plot on the left is that the polarization between the lambda hyperon and its anti-hyperon are very different when you go to lower energies. Now, if you look at the same data, but in mid rapidity, and you make a selection, and you can show the behavior of the polarization, not with respect to the collision energy, but with respect to centrality. Now, given the amount of work that people had done throughout the years, people knew that given that you have a picture of the collision in this kind of way, you know that if the collision is more central, you don't get to have a system which has lots of angular momentum to give, or to have available to couple to the properties of polarization of the lambda. So people knew that for more central collisions to the left of this plot, polarization should be going to 0. And some interesting things should happen when you are in the semi-central region, where again, you see kind of like a differentiated polarization for both lambdas and anti-lambdas. Immediately, there was a lot of work done by many collaborations with many ideas, in many interesting ideas, and people were producing their results, their model curves to try and explain this polarization. In particular, there was back then a heavy reliance on the fact that the system, when it reaches thermal equilibrium, then you can sort of assume there's also equilibrium between the spin degrees of freedom, and so the transference of spin from the system to the polarization of the lambda emerges as a kind of like a perfect transference of properties that of the system that is in thermal and in spin degrees of equilibrium. And so basically by this time, we have a well-established wealth of knowledge where the sources of vorticity in this kind of hydrodynamical models comes from the vector fields of these velocities that the fluid has, even locally. And using these velocity fields, you can create quantities that are also sensible to the properties of the system. In this case, you can create velocity over temperature. And with that, you can create like the relativistic version of the vorticity. It can either be the kinematic vorticity, where you don't introduce the role of the temperature, or it can be the thermal vorticity, which is more amicable to including effects of the properties of the medium. Together with this kind of framework, people usually use a kind of Cooper-Frye formalism, which is nothing else than like an expression that provides the equilibrium that to be able to translate the flow of energy and momentum in a continuous system into distributions of particles at the freeze-out surface. And this is very helpful, and it has provided many nice results. Except for us at this point, there's a list of like pending efforts from the theoretical point of view. And this is part of what I wanted to talk to you about. For example, the evolution of the quarks polarization in the QGP, the formation of the polarized hyperon from polarized quarks, which is this kind of I think is related to the question that Jennifer was asking me a while ago. The mechanism whereby you take some amount of polarization from the quarks and you give it to the hyperon. You assume you give it to the hyperon that you're measuring. What happens to the spin degrees of freedom if you include other kinds of interactions in the medium, in the hadronized medium that you're producing. And of course, things that have to do with the time that it takes for a system to equilibrate or provide spinorial properties to the extended volume, and if they hold until the end where there's actual conversion into hadrons in the system. Anyways, there's many things that we can discuss in these topics, but so the left part of this slide acknowledges that there's a lot of work done with a particular point of view, but in our model, we try to include some of these theoretical studies that we are doing in this discussion in the context of a core corona model. So if you are here still with me, that means that we can now discuss the recent work that we've done. This work is precisely taking on all the knowledge that we have so far in the description of polarization for lambda and anti-lambda, but including a way to account for the polarization that is not included yet in other models, but we can also discuss that in the end. In particular, we have this centrality dependent model, and in some parts of the polarization that we give to the hyperons that are being formed in this kind of model, we include the relaxation time for the time that it takes for a quark to align its spin with the information of the medium, and we take into account, of course, the behavior of this thermal vorticity in this both hot and dense QGP. We made an effort to discuss this in the context of the low energy collision energy range, because that's where the interesting things are happening for us now. If I want to summarize our main results and not leave it until the end, I just want to show what are the latest results by the STAR collaboration updated to 2021. And these were uploaded in July last year. And now we can see, I don't know if you remember, but before we were looking at data that was down to 7 GBs probably, but now we have new data back down here at 3 GB, and we see the wide differences between the tendency of the polarization for lambdas and anti-lambdas. We see that they peak at different energies, and we see a different behavior for each of them. And on the left, it's the prediction that we had from our model using only the ingredients that I'm gonna tell you about, and I'm gonna tell you what are the positive aspects of this model and limitations, of course. This model takes a couple of ingredients. We are modeling the overlap zone where these hyperons are being born, and this overlap zone is divided between a core and a corona areas or regions. For the corona, we are assuming that the main mechanisms to produce these lambdas are the mechanisms that we know about from a long time ago. I reviewed them at the beginning, where we can have several options on how to transfer polarization to the lambda, given that we can create lambdas by nucleon interactions directly. If you think about it in the simplest way possible, think about the corona being dominated by, let's say, proton-proton production of interactions to produce lambdas. And you can either have, let's say, a polarized lambda because there is radiation, gluon radiation, and if a polarized gluon is created in this kind of interaction, it may transfer polarization to the quark-antiquark pair that is created, that is part of the lambda. But you can also have some other mechanisms that are proposed a long time ago, the Grant-Mieten model, which is kind of like a way to transfer polarization to the lambda, given that there is kind of like a spin orbit interaction, given that the quark has some velocity parallel to the way that the momentum is changing when it's combined into the lambda. And so there's kind of like a spin orbit coupling appearing that is this kind of force associated with the velocity. But there are several in the literature, there's several ways to transfer polarization in this kind of, let's say, non-QGP context, which is the nucleon-nucleon interactions. And we will assume that in the corona, in our model, we are transferring polarization to the lambda in either of these ways. And I'll tell you why. For now, it doesn't really matter which one you choose. I'll tell you why in a moment. Now, for the core, of course, we just take whatever we had since the beginning when the QGP was being characterized with the strangeness enhancement. So for the core, we are thinking that we have the main processes that include gluon fusion, and we have to think of a way, a creative way in the core to transfer the polarization to the lambda. For example, we will do it here with the spin alignment of the strange quark in the lambda with some vorticity of the system, but we could also do it with some other property of the system, maybe a magnetic field or some other property of the QGP. So those are the two sources of lambdas that we detect, and somehow the contribution to the net or the global polarization of these lambda hyperons in the end will kind of mix the contributions from each of these regions. How is that done? Well, if you think that you can have a certain number of lambdas that I'm calling here just a generic n lambda, and you think of the total number of lambdas created as some of them coming from the core plus some others coming from the corona, then you can build the traditional polarization asymmetry, comparing the number of lambdas that are with the alignment of their spin in one direction with respect to the other direction. And you create this kind of asymmetry in order to build an argument on how the net polarization that we're measuring actually can have contributions, mixed contributions from the core and from the corona. And why is that? Well, simply if you substitute n lambda with the spin up and n lambda with the spin down in this expression, algebraically, you would get a very simple, I'm not gonna go through the details, it's just algebra, and you get a relationship between the total polarization of lambdas and anti-lambdas written in such a way that you have the contributions from the corona, which are going to be labeled by RHIC, because the main process that is creating these lambdas is kind of like a recombination process, and written in terms of the number of lambdas that are created either in the core or in the corona. And we see that we can sort of say a few things about the net amount of polarization for lambdas and anti-lambdas with an interplay of core and corona in both for both quantities. So it's not that the polarization of one kind of hyperon comes strictly from one region only. So it's a mixture.
I'm sorry.
Yes,
can I?
yes.
This is not clear. If you go back to your last slides, so I'm just trying to understand what kind of assumption you have for the lambda produced in core or corona. You assume that at least in the core region, they are still polarized because you assume the strange quark is polarized.
Well, I will tell you in a moment what we assume. So I need to tell you how I'm going to calculate the net polarization, but actually the rest of my talk is telling you exactly what do I mean when I say that the polarization from the core is different than the one from the corona. Because
yeah, but
indeed,
I know, but right now you're assuming the polarization for lambda in the core is different from the polarization in the corona.
I'm saying that the net polarization is just this asymmetry in the number of lambdas that are aligned one way or the other, but you can have lambdas from the core and the corona.
That's the definition of the polarization.
Yes,
true.
Yes.
Yeah. But you have not really.
I'm not really saying that this is dominated by one or the other right now, but okay, I would say.
I thought your next slide, yes. You are calculating polarization. And
no.
And then
here I'm not claiming anything yet, but I will claim. So here what I'm saying is that if you write the net polarization in terms of the comparison of the numbers of lambdas aligning one way or the other, this is just a direct substitution. What I'm saying is that we decided to rewrite this expression. I'm not assuming anything yet. we decided to write it in this way. The net polarization of lambdas has to come from a contribution of the polarization of lambdas that are created in the corona, plus something else that I will tell you in a moment what, over this common denominator here for the lambdas and here for the anti-lambdas. So I'm not saying anything yet, but I will in a moment. For example,
you have the subscript called QGP and recombination.
This is
it's called?
Yes, RHIC is for corona. Yes, basically because we are assuming a certain kind of process that it's, yes.
So your core is the QGP. Your
core is
corona
QGP, corona is RHIC, yes.
Oh, okay.
We should have done core or something, but corona also has the prefix core. This is why we can, yes, sorry. Anyways, so now I'm going to start making assumptions. So far we've not removed anything, but now I'm going to start saying things. For example, I'm going to say, well, actually, in the corona, if we model the corona as a region where you have basically something like cold nuclear matter, it's less efficient to couple the spin with the angular momentum. So on average, to start with this model, let's assume that the global polarization for lambdas and anti-lambdas, both of them, from the corona is negligible, right? That's to start. I'm going to tell you how we can relax this in the end of the talk, if I can manage to get there. But this is the first. Now I'm going to remove things from here. So I'm going to say the contribution to the global polarization of the lambdas and anti-lambdas created in the corona, actually the way to transfer spin there is not very efficient. So I'm going to say it's negligible for now, but I will tell you something later. So that's the first step. The next step in our model is to say, well, if you look at the numerator, you can see that there's a comparison between the lambdas aligned in one way and the lambdas aligned in the opposite way in the core, the QGP. And there's a similar expression for the anti-lambdas. So we are going to introduce the intrinsic global polarizations for lambda and anti-lambda in the QGP, given that we are comparing the alignment within the same region. So I'm gonna be discussing this object here, not in terms of each of the elements of the left part, but I'm going to be discussing them in terms of an intrinsic polarization for lambdas and the corresponding for anti-lambdas. And we will see in a moment that actually in intermediate to large impact parameters, we have this phenomenon in which the intrinsic polarization for lambda is bigger than the one for anti-lambda, and even more prominent for lower energy collisions, for lower collision energies. And this actually gives us an amplification effect for the anti-lambda polarization, which is what helps in the end in our results. So in the QGP, I'm not making assumptions yet. I'm just introducing the intrinsic global polarization. Now I'm going to start saying things about how we can create lambdas in the QGP and the corona. How can we create anti-lambdas both in the core and in the corona? Well, in the corona, we can think about PP data, and we can extract the number of lambdas and anti-lambdas. We can relate them through this omega parameter, and we are going to say that is the number of anti-lambdas that are created in the corona is proportional to the number of lambdas created in the corona, and the proportionality comes directly from what we know already from PP data. And we are going to do something similar in the core in order to reduce the parameter space, because we know that already I explained in the first half of the lecture that actually quarks and antiquarks are equally available in the QGP. So we can include a relationship between the number of lambdas and anti-lambdas in the QGP and extract the coefficient that relates them also from a particular model that we already know it works for other systems in the QGP. And of course, in the QGP, depending on the scans that you are thinking that you're going to use to explore the QGP, we are probing chemical potentials and temperatures of systems, and it matters the properties of this system. It will affect the number of lambdas and anti-lambdas that I can create. So we can have a particular way to calculate this relationship, this omega prime, using some thermodynamical equilibrium distributions that people have used in the past to describe what happens at freeze out. So far I'm going to, these are the main ingredients of the model. So let me summarize. I'm going to neglect the polarization contribution for lambdas and anti-lambdas that are created in the corona, but I still need to be able to describe how many lambdas and anti-lambdas I have in the core and in the corona, using on one hand, the intrinsic polarizations, and on the other, these relationships, or if you want to call them ratios, between the number of lambdas and anti-lambdas in the core and in the corona separately. So in the model, at the end of the day, we have inputs. We have three kinds of inputs: the intrinsic polarizations, these ratios, which are these omegas, and this red ratio, which is only the number of lambdas that are created in the QGP versus the one that are created in the corona. And for these three ingredients, I'm going to tell you where I got the information to include this in our model. How much time I have left, just to make sure I cover?
MaElena, I think that you have another 10 minutes left. I mean, maybe a little bit less. Is that going to be enough?
Okay, let me just summarize where we got this information from. So for the ratio of the number of anti-lambdas in the corona to the number of lambdas, we use PP collisions at low energies, and we make a fit. It was kind of hard to go near this threshold, but we managed that, and we have omega for that. For the ratio of anti-lambdas to lambdas in the QGP, we use the ratios of equilibrium distributions along the freeze out of the trajectory in temperature and baryon density that maximizes the difference between baryons and antibaryons. And we managed to extract omega prime for that in that particular case. For the intrinsic polarization is in the QGP, we use the knowledge of the fact that we have the evolution of these relaxation times given by the evolution of the system itself. We have work done, well, and not me, but people have worked on the estimating these relaxation times. And so the intrinsic polarization can be connected to the lifetime of the QGP and these relaxation times, and we get information from this calculation and from modeling the lifetime of the QGP and the volume, also from data. And so we have that as well. And these are the results for the relaxation time at different collision energies, and the results for the polarization, intrinsic polarization at different collision energies. So there's like a we expected to have these kinds of behavior. I can tell you if there's time in the questions, what is this behavior depending on the window of centrality that we look into. Now, for the final ingredient, which is how many lambdas I can produce in the QGP versus how many lambdas I can produce in the core, we needed to introduce like a geometrical element in this, right? Because once you define the core in a particular event, automatically you have the corona defined in that way as well. And it was known for a long time that there's a way to relate the average number of strange quarks available in the collision if you know how many participants are in the collision in this kind of Glauber picture. So the number of lambdas in the QGP is related to the number of participants in each of the collisions, in each of the events. And there is a critical density of participants that is needed every time you make a collision in order to create this QGP. So there's an on and off switch also to get the QGP on an event by event basis. So finally, the number of lambdas from the corona is controlled again by this integral over the overlapping functions in each event, and is modulated by what we know experimentally from the cross-section of PP collisions to produce lambdas. We know that from data, we make a fit, and we can modulate the number of lambdas created in the corona using this traditional geometrical Glauber kind of picture. So due to time, let me go to one before the final results. If you take into account all these inputs and you study, you remove the information of the intrinsic polarization, you study the ratio of net polarization to intrinsic polarization, then you see the competition between the information regarding where the lambda is created and how much that contributes to the net polarization. And there is a peaking behavior of this polarization, and the peak appears at different collision energies because of the competition of the particular ratio of the number of lambdas that you have in the core versus the number of lambdas that you have in the corona, and where it intersects with the sort of the inverse of 1 plus the same, where it intersects with this denominator, basically. So there is a competition of that behavior in the case of the polarization of lambda. And in the case of the polarization of anti-lambda, you have also the modulation of this ratio of transference of spin in one region and the other. In one case, in the QGP, we're using what we know from relaxation times and equilibrium distribution. And in the other case, we are just taking data from PP. With those ingredients, we create this net global polarization for both lambdas and anti-lambdas. The red band is for lambdas and the blue band is for anti-lambdas. With the available data that we had back then last year, from before the upgrade of data that started in the summer. And back then we had data available down to 7 GB. And we see that the bands that we can produce, the differentiated behavior of the polarization for lambdas and anti-lambdas that is created with this core corona model already gives us the possibility to describe this kind of different enhancement in this polarization for hyperons and anti-hyperons. The other thing we saw back then was that we have this peaking behavior, and we could move this behavior, of course, with the inputs of the model. And we communicated these ideas also with one of the people that were presenting preliminary results from HADES, which was back then it was in the Strangeness conference, and it was a preliminary result. It was 1 point here with error bars, and this is for gold-gold collisions at 2.4 GeV, and we just send them, well, we plotted and send them our result with this kind of low energy data using the same kind of model. And the idea is that once you choose your centrality range and the inputs that I just described, in principle, you can create these two bands, one for the lambdas and one for the anti-lambdas. So in principle, if HADES continues to take data, we should see whether or not this stands for those kinds of and of course, we're doing that for silver as well, because they told us that they are doing that with silver. And so finally, this is the main result of our recent work. So with this core corona model, we managed to have this kind of amplifying effect where we have differentiated polarization for lambda and anti-lambda with a peaking behavior, and this peaking behavior moves depending on the conditions of the system and the conditions of the competition between these mechanisms of production of lambdas, either from the core or from the corona. In fact, the range of centrality of these experiments are, let's say, on a sweet spot where you can have a very well-defined core and corona. And as soon as you start using this model for other centrality ranges, I'm just going to flash this. If we start to try to build the polarization of lambdas and anti-lambdas in centrality ranges that are trying to describe this polarization for peripheral or ultra-peripheral collisions. Of course, we ran out of, let's say, we ran out of core, and we have to improve the model so that the mechanism of not only the production of lambdas from the corona, but also the transference of spin polarization is effective when we go to more peripheral situations, like the data shows. There's this rising behavior, and then it keeps going up for upper 50–60% centrality, and so we need to keep learning what happens when we lose the possibility to create the QGP, and what kind of critical density we need to have in order to still have contributions from a core and from a corona, even in those situations. So I'm just gonna stop here and thank everybody for listening so far, and hoping that it was interesting for you as well as for me. So if you have questions, I'm available.
Excellent. Thank you very much, MaElena, for a great talk. We have time for questions. If anyone has them, please ask.
Yeah, I think maybe I have a couple of questions. I mean, it's pretty late. Maybe we can thank the speaker again. And my question, nobody, maybe you can continue after thanks speaker first.
But Xinyan, I want Ernst to ask his question. I'm curious.
Okay, Ernst, yeah, go ahead.
It's a quick one. First of all, thank you very much, MaElena. Is it correct that besides the inputs you have presented, there is no further normalization at all? So also it's directly, let's say, doable to compare between results you get for HADES and results you get for STAR, for example? There's no further fudge factor normalization or anything of that sort in here, right? Did I get that right or not?
That's correct. We don't have any more to move the curves around. What we just did was to make an adequate, so we modified the geometrical model to incorporate the sizes of the nuclei and the typical centrality ranges for those kinds of energies, but we didn't move, we didn't do any systematic normalization or anything in the end. So that was what came out of this overlapping analysis for those nuclei and for that centrality that they gave us. And in fact, we did it also for silver, because they were trying to do it with silver, and we sent it to them, but we haven't heard more from them.
Beautiful, thank you.
Thank you. It's so nice to see you, Ernst. It's been such a long time.
And in return, I'll turn on the camera quickly.
Yay, yay.
Oh, yeah. Can you steer us through again? I do have a couple of questions regarding.
Yes, of course. Sorry.
This is probably related to what Ernst has asked already. If I understand your model right, you actually assumed the polarization, is proportional, is given by the fraction z and z bar here, right?
In these plots where I'm doing like I'm removing the information of the intrinsic polarization just to check what is the competition between these ratios.
That's my question is, I mean, you in your model you have some kind of intrinsic polarization for the core, for the quark plasma, right?
Yes.
Which is given by z.
Yes.
And I don't really understand how do you calculate z? You relate this to some kind of relaxation time?
Yes. So in our model, the intrinsic polarization we get directly from this so the interplay between the relaxation time of the coupling of the way the spin of the quark is transferred to the, we model it using a kind of like ay, se me fue la palabra en inglés. So we calculate the rate of change of this amount of spin that the quark can provide to the hyperon using this calculation where you have the thermal vorticity, the volume of the system, and the propagator of this quark, and you learn what is the rate of the amount of quark spin that you can give to the hyperon eventually. And this rate is basically the inverse of the relaxation time. And
yeah, but this is okay. So even though this is sort of like you refer to this, the transfer rate for the quark go to the lambda, right?
Yes, we are assuming it's like a totally efficient way.
But
like
you still don't know the polarization of the quark in the quark plasma, because that's, you know, even if you're assuming that there is, you know, there is a spin alignment coupling between the spin and the vorticity. And then you still don't know what is the vorticity of the quark plasma and how that coupling is.
Yes,
right?
Well, in this work, the vorticity we extracted from work that was done by many people regarding the study of this vorticity, how it behaves for different centrality ranges. So indeed, we are.
So I see. That you didn't point out. So
no, I didn't point it out. It's in here in this calculation of the rate. It's in the paper, but we use vorticity from simulations as an input. Actually, it's a factor in front of this rate.
Okay, so you have the vorticity from some calculation.
Yes.
And that is a dynamical, you know, quantity, because it depends on the centrality, depends on collision energy too, right? So on top of that, you are assuming then you still have to have some kind of factor that is the coupling, what is the spin alignment, that, you know, the spin polarization of quark related to the vorticity, right?
Yes, so in principle, on a more sophisticated level, we should have a specific model for this coupling. For now, we just chose a very simple analysis where you couple directly the spin and to the vorticity. Yeah.
The lambda. Oh.
So I can show. Well, I can probably.
So this lambda is your polarization rate. Is that
yes.
Right? Because it is volume versus rate. Okay.
Yes. So the polarization rate, the engine of the polarization is this coupling between the vorticity and the spin of the quark, and it's done through this calculation of the rate using, you know, the traditional tools that you use for these rates. And the inverse of that is what we call the relaxation time, which is, of course, there's an interplay between this relaxation time and the lifetime of the QGP and the volume of the QGP. And
yeah, because even if even if you know vorticity, you still need some kind of calculation to turn that vorticity into the spin polarization, and then on top of that, you need this transfer rate to relate the spin polarization of quark to the final polarization of your lambda, right?
Yes, yes, I agree. Mm-hmm.
I see. Okay.
Mm-hmm.
Yeah. It would be nice if you can plot the HADES data on top of the star data, and it will be okay. Yeah. No, you have it already. Yeah. Here. No, the last one. Yeah.
Yes, in this one, you mean?
Yes.
The reason that we don't have it together with the star data was because maybe I'm wrong, but up until October last year, it was still preliminary. Maybe I'm wrong now in this moment, but it was, so we spoke with them and they still publish it in the proceedings of strange quark matter as preliminary. But still, we did send them the plots of this, actually these kinds of results with their own data for both gold and silver. And I mean, it's very hard. For silver, we ran out of QGP very quickly. We don't have a proper core for a very large centrality bin. So it's very hard to get anything useful for silver. But for gold, we did give it to them. And yeah, I don't know when it would be appropriate to put it in this same plot. I'm not sure.
Yeah.
Not yet.
Okay, thank you.
But it is connected to Ernst's question. So we can do it. It's not a matter of we fudging with any scaling parameter or anything. We can.
Okay, thank you.
Thank you. So I have a couple of questions for you, MaElena, but I'm going to stop the recording for us. And thank you again for talking with us.
Thank you.
Thank you very much.